in Haskell, create a monoid of a tree that, when concatenated, yields the trees appended at the root node. So let's take a look at what a monoid is. Haskell is a language based on set theory, and a lot of the times you'll have to prove that an element is of some type or some type class, right? So let's talk about what a monoid is. A monoid. A monoid is simply a container that contains a most natural binary operator called mconcat or mappend, and it also includes a empty element or identity element, right? Or identity element. So what this means is that a monoid is actually a semigroup. Now this might seem kind of confusing at first, but just think about these as classes that a thing could be, right? In a language like Java, you would have, like, for instance, a cat is an animal, right? And in this case, a monoid is a semigroup. But a semigroup only has one thing. It has the binary operator, the append operator, right? And what is a binary operator? Well, a binary operator just means it's an operator that takes two things, x and y, and it equals a z, right? That's all it is. It's that simple, right? So for instance, the integers under addition would be a semigroup, right? And what do I mean by that? The integers under addition would be, so for instance, 1, 2, 3, 4, 5, right? You have this set, but you also have the addition operator. And the addition operator in this case is the most natural binary operator. In this case, the addition operator takes two things, the addition operator, and produces a third thing. And what you realize is x, y, and z all belong to the same category, right? They're all integers. So the integers under addition would be considered a semigroup. Or let's say the counting numbers. And why do I say the counting numbers? Well, what happens if we throw in a 0, right? So again, we have a monoid, which is a semigroup. But what's the difference between a monoid and a semigroup? Well, a semigroup just contains the most natural binary operator. A monoid contains an identity element. And that means, for instance, in the natural numbers under addition, right? 0, 1, 2, 3, 4, right? Under addition, this is now what's considered a monoid, where the most natural binary operator is the addition, and the identity element is 0. Now, why is 0 an identity element? Identity just means that when it's applied to something else, the other thing doesn't change, right? So in this case, if you had the identity combined with an x, it should always produce x, right? In this case, it holds true for the natural numbers under addition, right? If we have the natural numbers under addition, we can have 0 plus 1, and that equals 1. We can have 0 plus 4, that equals 4. Or we can even have something like 4 plus 0, and that still equals 4. So in this case, we have an identity element, which is going to be the 0, and we also have a most natural binary operator, which is, again, the plus. All right, so let's actually now take a look at how we're going to implement MySum in Haskell. So if I make a quick mysum.hs file, we're going to start with making a new type, right? We're going to say new type MySum. It's going to be a MySum, and it's going to encapsulate an integer. Now, what this basically means is we have, you can think of it as a class in Java, right? A class that just takes an integer. It just stores an integer, right? And then we're going to derive show, which means that we can print this to the console, right? let's make an instance of a semigroup on MySum. Right, a semigroup on MySum, and what this means is we're telling Haskell that MySum is going to be a semigroup. Now, if you remember, a semigroup is what contains the most natural binary operator. Right, now this binary operator, let's stop Super Maven here. It's going to take a MySum, right? It's going to take another MySum, and it's going to return a MySum. Now, what this means is, if you're not familiar with Haskell, this is going to be a curried function. All right, it's going to take a MySum as the first argument, a MySum for the second argument, and return MySum. Or you can also think of it as it's a function that takes MySum and returns another function that takes an argument and returns a MySum as a return parameter. If you're not familiar with Haskell, definitely check out currying. Right. So we're going to take a MySum x, and we're going to take a MySum y, and then this is going to equal MySum x plus y. Right. Pretty straightforward. What this is saying is that our operator, when we get two MySums, we're going to return a MySum that contains x plus y. So now we already have a semigroup. If we come over here, right, and we GHCI and we load this MySum, we can get some info on MySum. Right, as you can see, it's a MySum that includes an integer, and it has an instance of semigroup, right? Which means that now we have this operator available. If we do MySum of 4 and we use this operator on MySum of 6, you can see we get MySum of 10, right? This is very simple, right? We're literally just defining addition, right? Same as you would do 4 plus 6, but this time we're saying it's a semigroup, just a fancier term for this addition. Right. Now, we already have half of what we need. All that's remaining is we need an identity element to make it a monoid. So to prove it's a monoid, right, we've already proved that MySum is a semigroup. So now let's do the proof that it's a monoid. And that just means we need a monoidal empty member. So this is going to be a MySum, and we're just going to define mempty as MySum of 0. So again, in our natural numbers, 0 is our identity element because it doesn't change anything, right? And now, as you can see, if we load MySum, if we get info on MySum again, we now can see that MySum is a monoid because we have both proven that it is a semigroup and it has an empty or identity element, right? And now, as you can see, we can still do MySum of 4 and MySum of, let's say, 9 this time. We get MySum of 13. Now, if you take a look at Haskell, right? If we take a look at the monoid, I think it's this one, right. As you can see here, we have a semigroup, right? And we have semigroup implies that you have monoid where you define an empty member. Now, what you can see here is we have this strange function, mconcat equals foldr mappend mempty. This seems very daunting at first, but it's very simple if we break it down. So let's go step by step. What is mappend? Well, this is just an abbreviation for monoidal append or monoid append, right? Then M just stands for monoid. So monoidal append is literally the exact same as the binary operator, except this time it's actually a function, right? So in Haskell, you have two ways of defining something. You can either define a function as something that takes x and y, or you can define a function as mappend x and y, right? So this is just the function in the style of, let me get my whiteboard out real quick. this is just the function in the term of, if I can draw. Yeah, this is just a function, right? So in Haskell, there are two ways of defining a function. You can say it's an infix operator, which means the operator comes between the two elements, right? Or you can say it's an f of x and y, and this is just equivalent to f of x, y. So it's something like this that you would see in like a C-like language, right? F of x, y equals c. So again, a bit of a tangent there, but mappend is the exact same as the binary operator, right? And as you can see, if we take mappend of MySum4 and mappend it to MySum9, we get MySum13 back. It's the exact same. All right, so now we understand what mappend means. We also understand what mempty is. It's the empty element of a monoid, right? mempty, right? So what now is foldr? Well, a lot of you have probably seen foldr before. It means fold to the right. And you can replace the word fold with reduce, and that might give you a clue on what's going on here, right? If any of you have worked with JavaScript before, you know that you can take a list of elements, right? You can pass it to a reduce function, right? And this function takes an A and B and returns what to do with it. So in this case, A plus B, right? And in this case, we have a reduction on 1, 2, 3, 4. And if you've ever done a bit of JavaScript, you're probably very familiar with a function like reduce, right? It simply takes A and B, and it keeps on adding it into it, right? So what reduce does, right? What reduce does is it starts with something like 0, right? And we have 1, 2, 3, 4, right? 1, 2, 3, 4. So reduce, we'll just say 0 plus 1 equals 1, right? Now our number is 1, and we'll get rid of 1, and then we'll add on 2, right? We'll get rid of 2, and then that equals 3, right? Next we'll get rid of 3, add it on to here, that equals 6, right? And then the last one's going to be 4, so 6 plus 4 equals 10. As we see back here, right? So reduce is simply just reducing all the elements into a single element. And that is exactly what fold right does. Fold right there's two of these functions, right? There's fold right and fold left, which are essentially the same thing. So the difference between fold right and fold left is just essentially which way it's evaluated, right? So if we have a list like 1, 2, 3, 4, and we want to fold a subtraction onto it, fold right, I like to think of it as it puts the parentheses on the right, right? So if we wanted to use fold right on here, it would essentially evaluate to 1 minus 2 minus 3 minus 4. Right, so this would be fold right, where all the parentheses on the right. Fold left does sort of the opposite, where it puts them on the left, right? So we'll do like 1 minus 2, right? And then we'll do minus 3, and then minus 4, right? This is what fold left would do. And if you actually evaluate these two have to be different values, right? This will be 3 minus 4, negative 1. 2 minus negative 1 is going to be 3. 1 minus 3 is going to be negative 2. So fold right, this is fold right, and fold left, right? And then this would be 1 minus 2, which is going to be negative 1, minus 3, which is sorry. This is we start with the 0 elements, right? So 0 minus 1 is going to be negative 1, minus 2 is going to be negative 3, minus 3 is negative 6, minus 4 is going to be negative 10. So this will evaluate to negative 10, and we can verify that in GHCI actually. So if we take a look at fold right, okay, how do we actually use fold right? Well, we can take some operator, right? Let's say plus. We start with an initial element such as 0, and then we're going to fold right onto 1, 2, 3, 4. right? That's going to give us 10. So as we saw before, if we change this to a minus, right, the fold right is going to give us -2, whereas the fold left, it's going to give us -10 because it starts in the other direction. Bit of a tangent there again, but now we know what everything means, right? So mconcat is just the generalization of mappend into a list of m, right? So as you can see here, Haskell is actually kind of interesting because Haskell, you have something called point-free programming, which makes it seem kind of weird, right? But essentially what point-free programming means is you can compose functions into other functions. So mconcat is this giant thing all smushed together into one function, right? And what you can actually think about it as is, instead of mconcat, you can think of this as mconcat x equals foldr mappend, it's getting kind of big, mappend mempty x, right? Now this will probably make a lot more sense. The x is left out because if you think about it, mconcat is the same function as this, and we don't really need the x in here, right? Because the x will be applied when the function is actually called, right? So now keep this in mind, right? mconcat x equals foldr mappend mempty x. Now, if you look back here, that looks a lot like what we had over here, which is the fold right. We take a function, a binary function, a function that takes two things and combines them into one, right? It has a binary function, it has an empty element, the initial element, and it has a list of things, which is going to be our x's, right? So now I hope you guys are understanding what mconcat means. It is a generalization of append to a list of items because here's a crucial thing, because we know the starting point. The empty element is the starting point, right? So we know the starting point, we know the binary function, and then now we can fold right that onto it. So let's actually make this, right? Well, actually, we don't have to make it because Haskell will infer it for us. If we take a mconcat, and we say a MySum of 6, MySum of 10, and a MySum of 15, as you can see, it simply adds them all together. And this essentially what it's doing is it's starting with the empty element. It's starting with 0, then it's adding onto it 6, it's adding onto that 10, and adding onto that 15. It's the exact same as the JavaScript produce. It just looks a little weird, but in my opinion, this is actually what makes Haskell beautiful. Because you can compose functions like this, it makes solving problems more of actually like problem solving, right? You get to decide on what functions to use to compose and figure out a problem. All right, so now if we take a look at our homework again, right? In Haskell, create a monoid. A monoid is just a semigroup with an empty element. Create a monoid of a tree that when concatenated, we know what concatenation is, we just did concatenation, that when concatenated yields the trees appended at the root node. So now let's actually implement this tree. Let's implement the tree. Let's make a tree.haskell, right, to do some experimentation with. Now, over here I have the code from Low Levels video. Right, I have the code from Low Levels video. If it would actually. Okay, so here is the code from Low Levels video. Right, we have a tree. And this is essentially a sum type, right? It means that the tree is either going to be a leaf or it's going to be a node with a tree on one side and a tree with another. Now, this is what Haskell is great at, okay? Haskell is great at defining recursive data structures, right? It is the absolute best at defining recursive data structures. So, if we take a look at this, right? Tree is either a leaf of A right? Where A is just a generic element. This A just means it's some type. Think of it as a type, right? It's a generic template you would see in C++, or some kind of generic you would see in any other language, right? So tree of A equals a leaf of A, or it's going to be a node. Actually, let me write it like this. Or it's going to be a node that takes a tree of A and another tree of A. Right. What this means is that a tree can be defined as just essentially a cascading tree of trees, right? A tree of trees. So let's think about this. A tree can either be a leaf of A, right? Let's assume A is an integer, right? Just to make things simple, right? So it can either be a leaf node, which just contains something like 4, right? Or it can be a node, right? It can be a node. Let's say a node is a box, right? Or it can be a node where it has 2 trees, right? Now, this right here is a tree, and this right here is a tree, right? Now, if you remember, a tree can either be a leaf, it can either be a leaf, or it can be another node. And if you've taken any class on data structures, right, you'll know that this looks exactly like a binary tree. Think about how hard it is to make a binary tree in a C-like language, right, where we have to define a pointer to the left and the right and everything. This is all you need in Haskell. It is either a leaf or it is a node, right? It is either a leaf that ends a tree, or it is a node that branches off. Beautiful. So we know this now, right? We know what a tree is. Now let's see how ChatGPT in low-level learning's video defined the semigroup of tree. This is something called pattern matching, right? Something called pattern matching. Now, what pattern matching is you can think of it like a switch statement. It's going to return the first thing that matches, right? It's going to look at what the data looks like sort of the structure of the data, and it's going to evaluate the first one where the structure actually matches, right? So in this case, the first statement here is if we have, if the left side is a node and the right side is a tree, we're going to return a node with the left of the current tree and the concatenation of the right of this tree and the other tree. Now, this seems kind of complicated, but if you kind of think through it, right? We have node L1, R1. This is just breaking down these 2 trees, concatenated with tree 2, right? So this is the case where we have some node, right? And we have an L1, and we have an R1, right? And then we have this concatenated with some other tree. We'll just call it a tree. Let's put it in a triangle. A tree, triangle is for a tree, like just a generic tree, right? In this case, we're going to return a new node that has a left element of L1, right? And a right element of R1 concatenated with T2, right? So this is going to be R1 concatenated with T2. Right? Now this is a recursive function because this recurses on itself, right? So this will call it back on itself because R1 is also a tree, right? R1 is also a tree. So this is a tree and a tree. Would you look at that? We go back to a function and it recurses onto itself. Now the second pattern here is if we have a leaf on the other side, right? If we have a leaf on the other side. So what would that imply? That implies that we are trying to concatenate a leaf, let's say with the number 5 in it. We're trying to concatenate this with some T2. We're trying to concatenate a leaf with T2. So we are simply going to make a node that has 5 on the left and T2 on the right. Right. Beautiful. So now this is sort of essentially our base case, right? When we eventually reach a leaf, it's just simply going to put the leaf on and not recurse anymore, and that's great, right? But some of my smart viewers will have noticed here that we have some warnings, right? And this is because ChatGPT actually made a mistake. These will never be reached. These clauses will never be reached because let's think about this. Why would we ever get to this clause? Well, it's in the case that T1 is neither a node nor a leaf. Well, T1 has to be a node or a leaf, right? We've already covered both cases. So we would never actually reach this clause. So this is redundant, right? Now, this one is also redundant because T2 could be a leaf, right? T2 could already be a leaf, which means that it would get matched out here before it ever matched out here. So this is also redundant, right? And then here's another problem that ChatGPT make. We have a leaf of undefined, and this is usually just a bad practice in Haskell, and it's just not recommended. Now, what would happen is if we tried to concat this, it would run into some pretty big errors, right? So I proposed some changes to ChatGPT's solution, right? I proposed some changes. First off, let's start by looking at the prompt again. Yields the trees appended at the root node. What does it mean to append trees at the root node? What I'm thinking is ChatGPT was overthinking the problem. We don't need all this fancy pattern matching. All we need is when we have some node 1, some node 1, and some node 2, all we need to do to append them is to slap them under a new node, right? So we should just, when we concat these two nodes, we should simply just return a node that has the left side as n1 and the right side as n2. Simple as that. Right. Now what this means is that we will need an empty node, right? We will need some node that indicates that it's empty. Think of this as like a null pointer in a C-like tree, right? So let's come back here, right? And we're gonna say data tree A equals, it's either gonna be an empty element, or it's gonna be a leaf of A, or it's gonna be a node with tree of A and tree of A. And we're going to derive show, so we can actually print it out in the console. Deriving show. Sweet. So now let's prove it's a semigroup. Now here's where the other thing comes in. Remember back in the beginning of the video when I said there's an identity element, right? An identity element. 0 plus 4 is going to equal 0. 0 plus 4 is going to equal 4. And 0 plus anything is going to equal that anything. So if we have an empty tree, and we concatenate it with some other tree, we should get that exact same tree back, right? That's what we should do, because that would satisfy the definition of a monoid, right? A monoid has an identity element that when concatenated with any other element returns the other element, right? It does not modify the second element. So that's why we have this empty right here. We have our empty already, right? So let's make a semigroup. Instance semigroup tree of A, where, right? Now we need to prove that it's a semigroup. Now how are we going to prove this? Let's start by defining the operation here. It's going to take a tree of A, and it's going to give back a tree of A. Again, we're going to use some pattern matching, but way more easy to understand. If we have an empty element on the left side, and we have a T2, we are going to return T2. Simple as that. If we have a T1, and we have an empty element, we are going to return T1. So if either of these elements are empty, tree of A. If either of these elements are empty, we are going to return the other one, right? And then finally, if we have T1 and T2, again, simple as we need it to be, we are just simply going to make a new node and connect them up. Right? We are going to make a new node and connect them up. It's going to be a node that takes T1 and T2. There we go. That's our semigroup. Simple as that. Instance monoid. That takes a tree of A. Actually, wait. While we're on this semigroup real quick, some of you might be thinking, what about if we get two empty elements, right? And this is a good question to think about. What if we get T1 is empty and T2 is empty? Well, it's very straightforward. T2 gets matched up and we return the empty element, right? So just to clarify that real quick. Where? To prove it's a monoid, we need an empty element. Now, what might you think the empty element is? Well, there's a pretty big hint. It's just empty, right? So now we have defined a tree, right? That is a semigroup, and because it's a semigroup, we can prove it's a monoid that has a mempty function, right? Now let's use this in action. Let's see this in action. In Haskell, create a monoid of a tree that when concatenated, yields the trees appended at the root node. Sweet. Let's just check that things are working right now. We're gonna load tree. We're gonna load tree, and we're going to say just to check things are working, leaf 4, right? That returns leaf 4. How do we build a tree? Well, we're gonna use nodes, right? We're gonna use a node, leaf 1, leaf 2, and this is going to be a node with leaf 1 on the left and leaf 2 on the right. So think of this as a node with 1 on the left and 2 on the right. Right? We just constructed the tree there. Instance semigroup tree A, where we have the concatenation function. What happens if we concatenate 1 with 2? We get a node with leaf 1 and leaf 2. Are you sort of seeing what's going on right now? If we have a node here that has leaf 1 and leaf 2, and we concatenate it with a leaf 3, we get a node that has a left child of a node with a left child of 1, a right child of 2, and this node has a right child of 3. Right? We have essentially built this. Right? Can you see how that translates over? Right? Now, let's prove to ourselves that the empty element does not modify the semigroup. Right? If we have an empty and we concatenate it with a leaf of, let's say, 10, it returns a leaf of 10. Beautiful. We've satisfied the definition of an empty element or an identity element. Now, here's the fun part. When concatenated, a monoid that when concatenated. Let's define a list, right? Let's say we have a list of trees, right? A list of trees. We're going to make the first one a leaf of just 1. Now, the second one, let's make it a little bit more complicated. We're going to concatenate this with, let's say, a node that has a leaf of 6 and a leaf of 9. Nice. A node with actually, let's make this one a leaf of like 7. Oh, what did I do? Trees. Sorry. Equals leaf of 1, a node of leaf 6, leaf 9. We're going to have a node of a leaf of like 10, and a leaf, or let's make it a node of leaf of 3, leaf 2. Close all these braces. Let's give it an empty element, and let's give it finally a leaf of 16. So now we have trees. Here's the great part. Mconcat trees. As we can see, we essentially start folding this tree onto itself, right? We have a node that has a left child of leaf 1 with a right child of all of this, which as you can see is all of this right here, right? A node of leaf 6, leaf 9 as the left child, and all of this as all of this. Node with a node of leaf 10, node leaf 3, leaf 2, there's left child, and finally we have leaf 16. And as you can see, the empty element gets discarded because it gets pattern matched out. So there we go. We have created a monoid. We have created a monoid of a tree that when concatenated yields the trees appended at the root node. And there we go. We have a root node here and all of the trees are appended to it. So here is my solution to the problem on Low Level Learning's channel. Thank you guys so much for watching. If you enjoyed, please leave a like. And if you have any questions about this, it's kind of confusing. I know I tried my best to explain it, but please leave a comment below if there's anything you would like for me to go over. Thank you for Low Level Learning for creating the initial Haskell video, which is a lot of fun. Please go check out his video if you haven't seen it already. It's pretty funny. And yeah, that's an explanation of the Haskell problem in Low Level Learning's video. And have a great day, guys. Peace.